So in other words, if I give you a graphing problem on an exam, you guys' first question is always going to be, do I need to show all these steps? And the answer is no, you only need to show the ones that I ask you to show. So I'm going to tell you which ones to do. For instance, I might ask you to do steps 5 and 6 independently of everything else. Because in fact, those are going to be the really important steps there. In other words, everything we've been doing in the last couple sections has been focused on what we're doing here in these steps 5 and 6. Right, so here, let's just go through these guidelines again. The steps here, starting with identifying the domain of or interval of interest. So figuring out, on what interval our graph should be graphed on. Second step is to look at any symmetry that we can exploit. For instance, is it an even or an odd function? Those might be useful for helping us determine the basic shape of our graph. Steps 3 and 4 are just going through and setting it up for the next few steps, but step 3, finding the first and second derivatives. Step 4 would be then setting those equal to 0 to solve for any critical points or any points where the second derivative is equal to 0 or undefined. So solving out when the derivative equals to 0 or where the derivative is undefined, those would be our critical points. And then finding the same thing for the second derivative as well. And then we're going to use those to make a sign chart for the second derivative, or for the first and second derivative. And those will help us determine what we need in part 5. So find the intervals on which the function is increasing or decreasing. So that would be where the derivative is positive for increasing, or where the derivative is negative for decreasing. Okay, so we're just analyzing the first derivative there for increasing or decreasing. Find where it's concave up, that would be where the second derivative is positive, or concave down where the second derivative is negative. Okay. The second derivative determines the intervals in which the function is concave up or concave down, right? So essentially creating our sign chart for the first and second derivative answers everything we need to know for part 5. And then using the information that we've gathered there, we can determine which of those critical points are going to be local max or local min, and also identify any inflection points. Remember, inflection points are where it changes from concave up to concave down or vice versa. So those would be points where the second derivative changes sign from positive to negative or vice versa. And then the last couple of steps here are just adding in some extra details. Are there asymptotes or end behavior that we should consider, and intercepts, in other words, the points where it crosses the x and the y axes. So those last two are not really related to what we did in the previous steps, but they're going to be useful for helping us to piece together a graph in the end. Okay, so again, it seems like a lot of steps, but I'd say if I were to give you an exam problem where I ask you to graph something like this, I would most likely just ask you to do these steps here, 5 and 6. Find the intervals where the function is increasing or decreasing, where it's concave up or concave down, and then identify any local extreme values or inflection points from there. Because those two steps there are essentially the main thing that we're going to focus on, or the main thing that we've been doing in the last few sections. So it's kind of putting all those pieces together. So we did this example at the end of class last time to remind you we had all this information given about a graph where f double prime and f prime satisfy each of these conditions here. Where we saw that if f prime is negative and f double prime is positive, then we know it's decreasing because f prime is negative and is concave upward on the interval from negative infinity to 0. So we can imagine it's going to be some curve like this. And then on the interval 0 to 1, it's increasing in concave upward, so it'll look something like this. From 1 to 2, it's increasing in concave downward, so it'll look something like that. Here it's decreasing in concave downward, so it'll look more like this. And then here it's decreasing in concave upward, right? Decreasing in concave upward, so it looks something like this. And then the last one is increasing in concave upward, so it looks curving upward like that. And so the actual graph here might have some shape that looks kind of like this, putting all those pieces together. Okay, so our goal will be for this section to kind of gather all this information from a function ourselves, and then use that information to piece together some graph like this. Although we're going to be gathering a lot more information than just these, but this is kind of the main thing that we want to analyze is all the information that we gather here. And yeah, here's essentially the same thing that we drew, right? The basic shape on each of those intervals. We saw that here at 0, we have a local minimum because that would be decreasing before and increasing after that point. At x equals 1, we have an inflection point because it switches from concave upward to concave downward. At 2, we have a local max because it's increasing before and decreasing after it. At x equals 3, we have another inflection point because it's switching from concave downward to concave upward. And then here at x equals 4, we have another local minimum because it's changing from decreasing to increasing. And here's their graph, but it's basically the same shape that we had, right? So notice that the y-coordinates here are not necessarily an important part. You can draw any graph that satisfies those properties. So the y-coordinates here are not really what matters, but the basic shape of the graph. So for the next few examples, we're going to go through the guidelines step by step and try and gather all this information that we can try and use to piece together a graph. So let's start with this function here, f of x equals x cubed over 3 minus 400x. Okay, it looks simple enough. We've got a cubic polynomial. But we're going to go through and collect a bunch of information about it. So let's start with the first few steps here. We're going to do all these steps here first. Remember the first step from our guidelines was the domain. Of course, here we have a polynomial. So the domain is pretty much all real numbers, nothing really to consider in terms of restricting the x values at all. So notice that doesn't necessarily help us when we're graphing it. Usually, if there are some restrictions on our domain, that might help us consider where our graph will be located. But here, there's no restrictions, so essentially our graph can be anywhere. What kind of symmetry do we have? Well, notice that this is actually an odd function. It has odd symmetry. Because if I evaluate f of negative x, because we've got odd powers on both of these terms, we can factor out the minus sign. So that means that we have odd symmetry here. So that means it's symmetric with respect to the origin. In other words, it has this this symmetry sort of like this, where if I rotate it 180 degrees around the origin, we get the same graph. So we know it's kind of like this odd symmetry type of graph. Let's compute the derivatives here. So I give myself a little bit of a space to squeeze in the derivatives. But it's nice because it's a polynomial, so the derivatives here will be pretty straightforward. First derivative, we'll take x cubed, so we got 3x squared over 3. So the 3's cancel, we get just x squared minus 400x, so 400 when we take the derivative. Our second derivative would be just 2x. So with that, now we can set them equal to 0 to solve for the critical points. So here we get x squared is 400, and then taking the square root, x is plus or minus the square root of 400, which is 20. It's 20, right? So those would be our critical points. And then for the possible inflection points, we'll solve when f double prime is equal to 0. Which of course 2x equals to 0 when x is 0. So that one's pretty easy to solve. So that's a possible inflection point. Again, we'll need to verify that it is in fact an inflection point. For the next step, we're going to now analyze the first and second derivative on a number line. So we're going to make a sign chart. So find the integrals or intervals where it's increasing or decreasing, and use that to determine and then also do the same thing with the second derivative to also determine where it's concave up or concave down. So we're going to make a sign chart for each of the derivatives. So let's start with f prime. So remember, it was equal to 0 at negative 20 and positive 20. Those are the critical points. So we'll analyze it on each of those intervals there. By the way, you may also notice that this factor is x minus 20, x plus 20. So if you prefer to look at these two separate factors that way, might help you do this step. Okay, so we see that the factor x minus 20 will be positive when x is greater than 20. Otherwise, it'll be negative on the other intervals. X plus 20 will be positive when x is greater than negative 20. Otherwise, it'll be negative on the other intervals, or just on the interval where it's less than negative 20. So you see, putting those together, it'll be positive here on the interval from negative infinity to negative 20. It will be negative here because you got a negative and a positive. So negative on the interval from negative 20 to 20. And then positive on this interval from 20 to infinity. Okay, so that tells us something. While we're at it, let's also make a sign chart for f double prime. Here, maybe even I can squeeze it under here and we can kind of think about how these two kind of go together. Remember, f double prime here was 2x, and that was equal to 0 when x is 0. We can easily see that it'll just be positive on this side and negative on this side. So remember, that means here it'll be concave down on this interval, concave up on this interval. These guys here will be, oops. So positive first derivative means increasing here, decreasing here, and then increasing here. So putting all those pieces together, here we've got increasing on the intervals, negative infinity to negative 20, and from 20 to infinity. And then decreasing between negative 20 and positive 20. And then it will be concave up on the interval from 0 to infinity, and it'll be concave down on the interval from negative infinity to 0. So actually what kind of helps here is also to essentially put these two intervals together, because now we, put these two sign charts together, so now we can kind of visualize, oops, how these two interact with each other. So we see that on this first interval from negative infinity to negative 20, it'll be increasing and it'll be concave up, right? I'm sorry, concave down. Right, from negative infinity to 0 is concave down. So it'll be increasing and concave down, so maybe something that looks like this. From negative 20 to 0, then we know it'll be decreasing and concave down. Something like that. From 0 to 20, now it's decreasing and concave up. So something like this. And then the last interval, it'll be from 20 to infinity, it's increasing and it'll be concave up. So it's increasing and concave up. Something like that. Just kind of helping us see what the basic shape is on each of those intervals. Notice here we've got essentially the same information that we had. Here's analyzing the first derivative, so we know those two critical points at negative 20 and positive 20 will also correspond to local maximum or local minimum values. We'll do that in the next step. And then here we have an inflection point at 0 where it changes from concave up to concave down. Here is the little picture that we just drew. So yeah, again, here we see a -20 will be our local max. Inflection point at 0, and then a local min at +20. So just based on that information, we saw that we have a local min at x equals +20. We showed that, right? So let's go back here. There was our local min. So let's find f of 20 to actually get the value on our graph there. So this is now going to be a useful point that we can graph when we're putting the pieces together. So we'll have 20 cubed over 3 minus 400 times 20, whatever that is. Okay, so this gives me, if I plug it in here, negative 5,333.3. So 1/3. We have a local max at x equals -20. So let's plug that into the original f to get a value that we can plot on our graph. Again, this is just getting us a point that we plot on our graph. So plugging in -20 here, we'll have -20 cubed over 3 minus 400 times -20. And actually, we can also use since we already computed f of +20, we know it's a symmetric, or it's an even function, or sorry, an odd function. So f of -20 would be the same thing as this, but with the opposite sign. So we can exploit the symmetry there and save myself the hassle of evaluating that. So those are the local max and local min values. And then we also have the inflection point at x equals 0. So let's get f of 0. In this case, is just 0, so that one's easy. Okay, so we've got some important key points there that we can include in our graph. We know those are the local min and local max points, and here's an inflection point. Let's look at the asymptotes. Notice that there's no vertical or horizontal asymptotes, so no asymptotes to worry about. So let's just think about the end behavior. So in other words, what happens as x goes to infinity or as x goes to a negative infinity? In this case, we can just look at how the x cubed function behaves. We know this end behavior is more or less determined by the leading term. We know x cubed will go to infinity as x goes to infinity, and negative infinity as x goes to negative infinity. So it'll go up on the right side, down on the left side. And then finally, we'll just solve some intercepts. We know our y-intercept actually is very easy. We've more or less solved our y-intercept when we found our inflection point. In general, find your y-intercept by evaluating f of 0. In this case, we get 0. To get our x-intercept, we solve when x cubed over 3 minus 400x equals to 0. I think I can simplify this a little bit. I can factor out an x over 3 maybe. Makes it a little easier here. Then we're left with x squared minus 1200. So x equals 0. That gives us the x-intercept that we already have here. X squared minus 1200 equals to 0. Gives me x squared equals 1200. So x equals plus or minus the square root of 1200, which is, let's see, that's 3 times 400, so it's 20 radical 3. Okay, whatever that is, 20 radical 3. So you can approximate that if you're curious, but I guess it's not so important right now. About 34.6. So, but you know, this is something we can graph just in that form. So now that we've collected all this information, let's piece together our graph. And important is to consider how we're going to scale it. Notice that we have key points at 20 and negative 20, so we want to make sure we scale it in such a way that we can fit those large values. So here I'm just going to scale it by tens. And remember that our local max and local minimum values were like 5,333. So they're kind of very far up on the y-axis. So we're going to scale our y-axis by like thousands or something so that we can fit everything on here. It's like 1,000, 2,000, 3,000, 4,000, 5,000. Same thing on the negative side. So I'm going to put down those key points that we found. We had 0, 0 was our x and y-intercept there. We have the other x-intercepts, say over here and over here, plus or minus 20 radical 3. We have the local maximum and local minimum values at negative 20, 5,333. So like up here would be our local maximum. And then 20, negative 5,333 would be our local minimum over here. And those are the key points that we collected. And then everything else is now just remembering how is it increasing, decreasing, concave up or concave down. And yeah, so it's pretty easy just to sketch the rest of it, just following those guidelines. We know it's concave downward for this side of the graph, and it's concave upward for this side of the graph. Okay, and everything else pretty much agrees with what we said. Increasing from negative infinity to negative 20, decreasing from negative 20 to positive 20, and then increasing again from 20 to positive infinity. So just making sure here we're getting the right curvature. It's curving downward here, and it's curving upward here. Okay. So we collected a lot of information just to get this very simple basic graph, but notice that it includes some key points here that will make the graph, very accurate. For instance, it's got these local max, local min values, inflection points, and intercepts. So those key points make my graph very accurate. It's not like just a rough graph here. It's a very accurate graph. So there's a more detailed graph, or I guess a more pretty looking graph, but notice it contains the same details that we had in our graph. Not really any different. Okay, so let's see if we can work through another example here. I know these examples take a long time to go through all the steps. So let's try and get through some of the steps here. It says, use your graphing guidelines again to graph f of x equals 10x cubed over x squared minus 1. Okay, so I'm going to go through the same steps again. Notice that in this case, our domain has some restrictions because we have x squared minus 1 in the denominator. So we know that x squared minus 1 should not equal to 0. So therefore, x cannot equal to plus or minus 1. So therefore, the domain will be only values excluding negative 1 and positive 1. Okay. Notice also we have some symmetry here. If I look at f of negative x, notice that negative x cubed, we can factor the negative out from there. Negative x squared just gets rid of the negative. So taking the negative out from the numerator, we get the opposite of our original f. So this has again, the odd symmetry. So again, remember that's symmetric with the origin. Okay, let's, hopefully I gave myself enough room here to work out the derivatives. Let's try and squeeze that in here. Notice that we're going to have to use the quotient rule to do the derivatives. For the first derivative, we'll take the derivative of 10x cubed, will be 30x squared, times the denominator, x squared minus 1, minus the derivative of the denominator is 2x, times 10x cubed in the numerator, divided by x squared minus 1 squared. And let's see, so that'll, when I simplify, we'll have 30x to the 4th minus 30x squared, and then minus 20x to the 4th. So I think we get 10x to the 4th minus 30x squared when I combine the terms upstairs. So then I can factor out a 10x squared, and then I'm left with x minus 3. Okay, so there's a simplified form of our first derivative. Let's do the second derivative. So actually, what might make it easier for me to do the second derivative is to use this form of it that we have here before I factored out the 10x squared, so that way at least I don't have to do the product rule in the numerator. So I'm going to look at this form of it here. So that when I'm taking the derivative of the numerator, it'll be 40x cubed minus 60x times x squared minus 1 squared in the denominator, minus, and then for the derivative of the denominator, we have to do a little bit of chain rule. So that'll be 2 times x squared minus 1. And then chain rule, so we're going to multiply by the derivative of x squared minus 1, which is 2x. And then multiply that by the numerator, 10x to the 4th minus 30x squared. All over x squared minus 1 squared squared. Okay, so that's doing the second derivative. Notice a bunch of things we can simplify. For instance, I can try and factor something out from the numerator here. Actually, that might make it a little bit simpler. So we've got x squared minus 1 factors out. Leaving me with 40x cubed minus 60x here. Times x, another factor of x squared minus 1. Here I factored out this x squared minus 1, so I'm left with minus 4x times 10x to the 4th minus 30x squared. Okay. All over, here we'll have x squared minus 1 to the 4th, and that's where I can actually divide out one of these x squared minus 1s with the x squared minus 1 that we factored out. Okay, and actually from here, it would require a little bit of foiling. And then combining like terms. So if we go a little bit further here, we can do some foiling and combining the like terms, but let me see. So we'll have just, let me kind of write it out really quick. 40x to the 5th minus 40x cubed minus 60x cubed, and then minus or plus 60x. Okay, so that's foiling here. And then here I'll also foil here, so minus 40x to the 5th, and then minus 4 times 30, so negative 30, so plus 120x cubed. Okay. Downstairs we got x squared minus 1 to the 3rd. Notice here actually some of these terms go away. 40x to the 5th minus 40x to the 5th, those are gone. Here we'll have minus 120, or sorry, minus 100x cubed plus 120x cubed would leave me with 20x cubed. And then factoring out a 20x from the numerator, I'm left with x plus 3. Anyways, let me stop there. We can pick this up next time. But now we've got it set up, f prime and f double prime. So we can go through and now quickly find the critical points and inflection points. Notice that once they're in these factored forms, it's very easy to get the critical points and inflection points after this.